let's talk about an explicit relationship. Now, an explicit relationship in mathematics, all this really is it is a function. It is, sorry, is this going okay? Or is it slow? All right. It is basically a function where a variable is solved for. In other words, we can define one variable in terms of another. Whoops, sorry. Let me get this out of the way. It defines one variable in terms of another. Examples, something like y equals x plus 3, our normal equation of a line. We can go even fancier by getting triggylicious with it, like sine x plus the square root of x squared minus 4. These are all examples of an explicit relationship. In other words, y is being defined in terms of x. Y is defined in terms of x. Y is explicitly defined in terms of x. We can go outside of algebraic and go to geometric. Area of a circle, pi r squared. Area is explicitly defined in terms of the radius of a circle. These are what we call explicit relationships. And they're most likely our functions that we deal with. Now, in an implicit relationship, these are where we don't explicitly define one variable. So, in this case, variables aren't solved for. Like over here, where I have y equals something, a equals something. Here, variables aren't, whoops, terrible. Now that's on my video. That's going to be for everybody to see for all times. Variables aren't solved for, are not solved for. And there's a reason for this. One, we can't either solve for them, or two, don't wanna. Okay? An example of an implicit relationship would be like x plus y equals 7. Even though this is a line, just like this one is, this is considered an implicit relationship, and that is because not one variable is not in terms of another variable. Y isn't in terms of x, and x isn't in terms of y. I could make this explicit by solving for y, making it 7 minus x, and then it would jump into this column. So this is called an implicit. Now, other ones could be examples like x squared plus sine x minus y cubed plus 4y squared equal to, I don't know, pi. I'm just making this stuff up as I go along. So this is an example of an implicit relationship. What I want you guys to notice is try solving for y here, or try solving for x in terms of the other variable. It ain't going to happen. Okay? You can't solve this one. So today's lesson is, well, how do we solve for functions or relationships, where a variable isn't solved for? Another example could be this one, sine x cosine y equals root 3 over 4. I had an ex-girlfriend in college give me this question right here. We'll talk about this one later on. So today what we're going to do is we're going to learn how to find the derivative of equations that are not defined as functions. In other words, implicit relationships. It's very important to note that many of our derivatives will be defined in terms of both x and y. We are going to use Leibniz's notation. You might remember that. That's that dy dx. And the reason we like this is very simple, is that it asks how the changes in x affect the changes in y. In other words, what dy dx means for us is how it asks us, how does y change as x changes? Later on, it's going to allow us to really think about these x and y independently from each other. So what we're asked to do today is to find the derivative of a function, dy dx. But before we do that, let's talk about what dy dx really, how we kind of apply this. The derivative of y. You don't have to write this down, I just want you to watch this. The derivative of y. Okay, if I find the derivative of x squared, what is that going to equal? Just 2x, correct? Remember, we're finding the derivative with respect to x, and that's the big thing. We're finding the derivative with respect to x. So this is x squared becomes 2x. And that works for anything with x's. What's the derivative of sine of x? We know that's cosine of x. But what happens if we want to find the derivative of y? Well, the derivative of y will be how y changes with respect to how x changes, dy dx. So the problem occurs when I have something like this. What if I want to find the derivative of y squared? That's a little bit tougher to do. It's not as simple as just saying, oh, it's 2y. So to answer this question, we're going to go back to our homework. We all know that if I have y is equal to f of x. Correct? Remember that from Algebra 1? So if I have y squared, that's going to equal f of x squared. Everybody kind of following along here? So if I want to find the derivative of y squared, well, we know how to take this derivative. This is our super duper blooper trooper chain rule. So this is going to be my derivative of my outside, 2 times f of x. But now I got to take the derivative of the inside, which is f prime of x. We saw these on our homework last night. We saw these in our notes the other day. This is that analytic derivatives. So another way to write this is, well, the problem is with Newton notation, it's f's. It's a lot of parentheses, a lot of x's, right? I haven't seen that many x's since my college reunion. I'm joking there. I was kind of a loser in college. All right. So when I take the derivative here, I can do the same thing. I'm going to use my chain rule. I'm going to drop the 2 down. I get 2y. But now, remember, this y is f of x. I have to find the derivative of y with respect to x. So I tack on a dy dx. And that's what this says right here. 2y dy dx. So when we take the derivative of anything with a y, we get dy dx. We're going to talk a lot about that today. So let's go ahead and look at some examples right now. We want to find the derivative of 3x squared. Now we all know this is just 6x. So I'm going to go ahead and take the derivative. Well, the derivative of y, this is our new rule, is just dy dx. That's my new rule. The derivative of y is dy dx. Remember, what this says is we want the change in y with respect to the change in x. That's what this says. I want the change in y with respect to the change in x. Over here, when I take the derivative, I'm going to use my power rule. Now this becomes 6x. Now I'm going to get really funky with this one, okay? Watch this. I can take the derivative of x. It's still kind of a chain rule. We just don't ever do this. I want the derivative of x with respect to x. See, I'm taking the derivative of everything with respect to the change in x. So this says take the derivative of y with respect to x, so I get dy dx. This says take the derivative of x with respect to x. Well, that would be dx dx. We never do this, okay? I'm just showing this example. So this becomes 1. When we do related rates, though, next week, we're going to talk about this again. So my derivative, dy dx, is just 6x. Now, I know this one you all finished like in a second, but I just want to show you what we did here, we're going to apply to all of these. So let's take a look at number 2 real quick. Let me zoom in here real fast. When we take the derivative, anything that has a y, I'm going to treat this like a chain rule. I'm not going to worry about the x's. Remember, what this is really saying is the following. F of x cubed plus f of x squared minus x squared equals negative 4. I know this is a chain rule right here. We're just using y's instead of x's because they look nicer. So when I take the derivative, I'm going to get this 3y squared, but I got to multiply by the derivative of y. That's my chain rule. See, I would get this 3f of x squared, but now I got to take the derivative of f of x. Well, we're using y instead, so that just becomes dy dx. Plus, I do the same thing here. This becomes 2y times dy dx minus x is, we're just normal derivatives, 2x equals, and don't mess this up. The derivative of 4, this is a constant, so it's just, of course, 0. All right. Now, I'm going to solve for dy dx. Or I like to say, dwidx, if you spell it. Dwidx, get it? Moving on. So, to do this, anything that has a dy dx will stay. Everything else goes over. So we get 3y squared dy dx plus 2y dy dx equals Dos Equis. Stay nerdy, my friends. Now, to solve for dy dx, I'm going to factor out my dy dx, and that's going to give me 3y squared plus 2y equals 2x, and therefore I can now solve dy dx, ran out of room, is 2x divided by 3y squared plus 2y. And there is our, just ran over, and there is our derivative right there.